There we go.
Okay. Good afternoon or good morning or good evening. I don't know, but my name is Hamid Arastoopour. I'm the Linden Professor of Engineering. Good morning or good evening. I don't know, but my name is Hamid Arastoopour and Biological Engineering. I'm the Linden Professor of Engineering and Aerospace Engineering. My appointment is I'm also running what is called Biological Engineering, which is the Wanger Institute for Sustainable Energy Research. And we overlook. I'm also running all the activities related which is the Wanger Institute for Sustainable Energy Research, and we overlook all the activities related to the energy and water. Energy and water connects major things. Basically, if you look at sustainability, although it's covered the economy, energy and water connects major things. Basically, I start from the third one, which is sustainability, although it's covered the economy, but preservation of the resources and environment. And I start from the third one, which is sustainability. And also, it has sustainability is preservation of the resources and environment, economics and climate change, and also technical. And also, it has three legs: social impact. So we wanted to have processes which is sustainable, and also technical, and which is also has a positive impact processes which is well-being of the human beings, and also energy and water positive impact on availability of the clean water and life. And medicine is very critical. Also, energy and water touches health. The other thing is security. Water and medicine is very critical in the sense that and water plays significant role. We are taking the other thing of that. You always go home, turn on air conditioning, in the sense that the lights and energy is there. We are taking this is called energy advantage of that. You always and go home, the food security, turn on air conditioning, turn on the lights and energy is there. Not only for the places that everything working fine, but and the food security, water which is experiencing not only for the places that everything working fine, but for the rest of the world because of this impact, which is experiencing a lot of dry out. Well, if you look at some of these pictures here, you will see that this is the prediction by well, if EIA, you look at some of these international agencies, you will see and you will see by even the prediction by EIA, there are significant amount of international agency, and you will see by even the natural gas is 2040, there are significant amount and it's important of the natural gas because natural gas has less carbon and hydrogen, therefore it good role, and it's important. If you look at the water consumption, natural gas has less carbon per capita per person. Therefore, this is in the United States. This is in Europe. Look at the water consumption. I don't have in Asia, but all these people this is in the United States. If they want to spend, this is in Africa. That much water. I don't have in Asia, but all these people need to huge shortage of water. They want to spend, and still we have a huge that much of water like we do in the United States. The same thing with the energy. This picture is not clear and shows that a lot of dark spot here, and the impact. The same thing with the energy. Dark spot here, which is the China. Shows that a lot of dark spot here. They're going to come back. And they use energy when they use energy, which is the China, some of them in India, so much CO2. They're going to come back again and use energy when they use energy. We don't have enough, and most of them use so much CO2. For example, again, CO2 consumption, water is very critical. Production increase for agriculture. For example, some of the CO2 consumption. Ice on top of production increase and bring a lot of flood to melt India. Some and after that shortage of water. Ice and in on India, top of Himalaya and bring a lot of flood to portion India. And after that shortage of water. And in India, where the most they use tremendous portion, means so it's a very critical 85-90% of water for see the connectivity where the most of the carbon CO2 production. So it's a very critical for us and that well-being see the connectivity. What is climate change, CO2 production, indicators? Water consumption, one of them is temperature. And well-being of the temperature is going. Even this is what is climate change? Temperature indicators. Well, one of them is temperature. As you can see, the temperature is going. The environment small increase and the absorption or desorption means significant effect in the sun characteristics of the environment. And you will see that also the sea level is going to go up. Sun arrays. Look at this is a nice picture. It used to be. And you will see that also the sea level is going to go up. In Alaska, look at this is a nice picture. It used to be all ice because we are going to get less and less in Alaska, but it's really bad for the climate change. What's climate change? Because we are going to get less and less portion you will see here is CO2. And the climate change, what's climate change? This is going to have a big small portion. One of the effects is flooding. Means the places that is going to have not rain was raining a lot. One of the effect is the places which means the places become drier. Was not rain was raining a lot. Will rain more. Dry surfaces is going to become dry, like become drier. And so that rains huge because on the dry surface, which is going to have a lot of the flooding water, so and also countries have a lot of water, like on the countries which does not have a lot of the water, and also constrained by the average in temperature. This is the problem. Density probability distribution. The people, small changes in temperature, climate change have much average in temperature. Changes is the problem. In extreme cases, are a very small changes in temperature will have much. So change of temperature is not in a same extreme cases are a very. You have to look at the extreme conditions of cold and hot. Change of temperature is not places same everywhere in the world. You have to look at the extreme and also conditions. There are species and hot, and these are the places try to live getting at different temperatures and create and also new kind there are species with temperature change species. That's why we established this Wanger Institute for Sustainable Energy Research at IIT. Supported by that's why we established from Mr. Wanger Institute for Sustainable Energy Research at IIT. So supported by the very different organization than Mr. For example, the colleges or the departments you have. So they are vertical. You go to very different organization than, and for example, you go to colleges or the departments you have. They are vertical. You go to. This is not that way. It's an umbrella organization. That you go to mechanical, you go to biomedical, you go to chemical. So when you look at this is not that way. It's an umbrella identify the problem, look and at then the energy, go to the faculty and sustainability, and bring the. So when you look at this issue, who would like to identify the problem and then go together to the faculty internally and bring the different professors faculty who would like to work with other universities, laboratories, work together. Internally between different we also have two boards. One is the faculty board, the other one is external advisory board. Which we are also at all our activities. Two boards. One is the faculty board, the other one is external advisory board, which look at all our activities. More than 85 faculty affiliated with this. They are from all the colleges across the university. There are more than 85 faculty affiliated with this. They are from all the colleges across university. On a least cost pathway toward future sustainable net zero carbon economy. On a least cost and two things toward future sustainable climate change, net zero carbon economy. I mean, some places and two things on the other place. Focusing on climate change, you want a least cost pathway. I mean, means economically feasible is important. Future sustainable, but war you look at you want net zero carbon pathway, and that's economically feasible. I call it future sustainable. Not there, war, and it takes time to get net zero carbon economy, and so that's the wiser mission. I call based on that continue improvements of humanity time to get there, and to be a pathway to sustainable economy. Wiser mission again, based on that continue improvements of humanity, water shortage, and to be a pathway to sustainable economy. We have a lot of programs, as I mentioned. Undergraduate combating. We have a lot of programs called IPRO, Interprofessional program. We have a lot of programs. If you're undergraduates, we have a lot of programs called IPRO, Interprofessional program, which is focused on energy and sustainability or other fields. We have a specialization on energy and besides your field, get a specialization. You can be as there are a lot of focus topics, courses in this area. And besides your opportunity to do undergraduate research, focus topics, and the whole campus of IIT in this area. Opportunity to do undergraduate research. And the whole campus of IIT, we have a lot of IPRO interprofessional projects, which is students from engineering, science, as IPRO. We have a lot of IPRO and try to solve interprofessional project. This is what called engineering, IIT means that we all get together and try to solve produce. This is what called farm IIT. Urban farming means that IIT we try down the produce CO2 to create the urban farming at IIT to cut down the in campus of IIT CO2 you have a living lab, and we have one of the first to have the campus of IIT We have a living lab. We have one of the stations to have the charging station. We have microgrid, solar panel everywhere. All the stations about the charging station. We have U-farm and on and solar panel everywhere. One that the students get involved. We have composting. Also, we have few things. U-farm and I brought up. There are IPRO group of students get involved. Are working on the hybrid. Also, we have few things. And they have gone to the national competition. There are IPRO group of students. Few years ago, I wrote a book on the hybrid electric car, and they have gone to the national competition. And we wanted to go to the high school. A few years ago, I wrote a book on sustainability for kids, and provide opportunity for them to learn high school, expressing in an online school in order to. We offer also for our students distinguished lecture series for them to learn, and we invite our competition. This we offer the also for our students distinguished lecture series from Enel Lab. We invite our competition. From Stanford, this is the director of the energy lab at MIT. She's the chair of the mechanical engineering lab from Purdue at MIT. From Stanford, they are the people who work on different aspects, and we try to exchange ideas and learn from each other at MIT. So they are the people who work on different aspects. Well, and we try to. This is a very complicated problem. In order to look at it, you don't know what you do. What is our current need? Short term, this is a very complicated problem. In order to look at it. Our short term is basically energy efficiency, and long term, and try to connect these things. We started at the short term, at the very low level, basically energy low hanging fruit, we call it. Means that we started at the very low level, enhancing the efficiency of appliance and energy management, recycling, and also starting at the much larger one, enhancing the efficiency of appliance and energy management. Means that and also starting at the much larger one, secure and reliable electricity, microgrid or smart grid for the communities. Also, we work on the project on CO2 and reliable electricity. Up a lot of things. And also, how do we use? Also, we work on the project on CO2 capture because we have messed up a lot of things. And the long term, and also how do we use when we capture CO2? Solar, how to use major part. Energy storage, and the long term is we are focusing on wind and synchronization of these major part. Energy storage. Because we have to bridge between this short term and long term, and synchronization bridge of basically AC energy is natural gas. We have to bridge between this short term and long term, and our bridge basically is natural gas, and sustainable is much more relevant in the United States. Hydrogen. But it could be nuclear energy going to the pathway of decarbonization and sustainable bridge to the future of hydrogen, or going to create a lot of support for the faculty to work together to the future. We are focusing, one of our major focus. We create a lot of support for the faculty and the computation. We are using all kind of focusing. One of our major focus is AI, computation, processing, and the computation, chemistry, biology, and in application a lot of things. Carbon capture, AI, wind turbine, data processing, molecular dynamics, chemistry, biology, all kind of application a lot of energy storage, capture, sustainable built environment, concentrated solar production, gas turbine, all kind of energy. So we work a lot storage, we do a lot of sustainable built environment in order to broader umbrella areas that we are working. So we work a lot of one is the smart city with focus in the city of broader umbrella areas that we are working. We look at microgrid. One is urban smart city with focus in the city of Chicago. Built environment. What we do in the smart city, we look at microgrid, and also CO2 emission. Urban agriculture. This is one. The other one is a pathway toward a sustainable future economy, CO2 emission reduction. Our major work we have in energy. The other one is a pathway toward a sustainable future economy. You know, is the concept of the solar major work we have in energy storage, and also renewable bioenergy, which is and natural gas and not as solar energy, future energy, but as and also substitution bioenergy to natural gas, not as a future energy, but as a substitution. Let's focus on few of the projects on the pathways toward the CO2 capture. We try to capture it this way. Let's focus on few of the projects, so we will build a lot of processes. So if you look at, try to understand what is CO2 this way, didn't work. So if you look at this build the gray one and the brown one. So if you look at the brown one, to understand what is CO2, that if you look at this gray, the gray one and the brown one. The brown one cutting the trees, CO2 that we produce and forest areas, then generate. We would not by the cutting the trees. if we wouldn't cut the trees and forest areas, and the gray one, which is the huge one, would not is what we created. CO2, therefore, additional CO2. We create much and the more. Gray one, which is the huge one, is what we created. Flaring and cars and all kind of things. We create much more. And if you look at the natural gas comparison with cars and all kind of petroleum or coal, you are producing. And if you look at the natural gas comparison with the petroleum or coal, you are produce twice as much natural gas. Therefore, with the liquid fuel and with the coal. If you look at who's producing a lot, this is natural gas. CO2 emission that China produced. This is USA, Europe, who's producing a lot, and the rest of the world. But CO2 emission that China produced. This is USA, but statistics. India. You have to be very careful. This is the one per capita China produce means divided by population much. But statistics, if you look at US, this is her person. The one per capita produce more CO2 means divided by population in tons. If you look at US, what's the solution? Per person, we have at IIT produce more CO2 for CO2 capture. That we are using a reactor. We have at IIT in this reactor program for CO2 which capture. Is working here, we are using a reactor will come here, and in this reactor, go through that solid will come back. Working here, we will get the from exhaust gas come here. Then the solid will come and regenerate. That solid will come back. Why we regenerate? We will get the this is about 15% there. And then the solid will come and regenerate much higher concentration of 80. Why we regenerate? Because in order this is about 15%, and then we can utilize that. We wanted much higher concentration to do that, of 80-90%. You have to prepare solvent in order CO2 to be useful. And then we can chemistry-based. We have a lot of engineering to do that, take care of the system and the process, and the design and the modeling. Chemistry-based, validate. We have a lot of engineering to take care of and the system and the process to the high pressure design and the modeling. This is called validate our model. When we get this high concentration to the high pressure of the CO2, then we can use CO2 when we get this high concentration, use of some energy from sun, basically CO2. Then we can use CO2 into CO with the fuel, use of some energy and utilize the fuel, basically, and then produce CO2 convert CO2 into CO to the fuel, so that and CO2 utilize the fuel, high concentration and then produce CO2 can be converted the whole process of utilization. That so the CO2 which is high concentration produced can be converted through this process, and or the professor excess CO2 can be sequestered into sequestration, means put it on the ground, or and if excess CO2 can be captured with compressed pipelines, put it on the ground, geological storage. But if you look at the whole process, we try to be much smarter, not putting directly in geological storage. Only the excess one we put here. We try to be much smarter. And what happened when you directly in geological CO2 in? Only the excess one. This is the number of years that you inject CO2. And what happened when you put the old CO2 in? This is the number of years whether into the CO2, whether into the old reservoirs, or whether into the ocean, into the dump. Whether as soon as you go underground, initially it's very critical. From year 1 ocean into the dump, as soon as you go underground, because initially it's very critical. From year 1, we try to 10, trap it in a structure. If you don't trap because it will come that out. May and CO2 is much worse. We try to trap it in a structure. If you don't trap it, it's a waste of energy. And CO2 is much worse. If we can capture it, trap it in, and it will come out to the it's a residential phase change and trapping. If we can capture it, trap it, it goes to the and after 1,000 years, residential phase change and trapping between the converted solids. So it takes years to convert 1,000 years. It really can go to become very stable and convert to the mineral. That's about so CO2 it takes years to convert to mineral. You probably heard about smart grid or microgrid and a smart use of electricity. Basically, you probably heard about smart grid or microgrid and a smart use of electricity, the electric provider. And we have a plug which communicates with the tell them, okay, system what are the necessary, what are the unnecessary, and this plug electricity that we use, for example, tell them, okay, and what are the necessary, what are the unnecessary at the peak time, electricity that we use, communication, for example, washing and drying, you can turn it on, when you can turn it out, of course, at the peak time, and this communication will tell us when. And it's really communication, of course, a lot of data processing in order to manage that. And it's really communication consumption and a lot of data processing. The management will reduce it significantly. We are wasting a lot of energy at home, all of us. The management will reduce it. Of course, installation is important. We are wasting a lot of generation on site is important. All of us. But of course, installation is important. Of course, the generation on site is important. The Galvin Center, but under we lost a lot of energy. At IIT, we have done a lot of work to divide IIT into different loops. Under instead of electricity coming from one side, we have done a lot of work. We divide IIT into different loops. One is color. One instead of electricity coming from one side, green, and leaving each side. We put if something happened, for example, in this building, this loop will be out of the system. The rest of and the campus loop or the macro grid. If something happened, for example, in this building, this loop automatic will be out of the system. The rest of prescriptions of the fault will be done. Otherwise, the building will be identified. Automatic only the building will be out. Prescriptions of the fault will be done. Otherwise, the building will be identified, and only the building will be out. At IIT, we have a lot of instead of this whole macro grid, we have something called nano grid. At IIT, we have a lot of solar on the top and supported by the battery. We have something called nano grid, and we can provide electricity, solar on the top, and supported by the battery system. Can store it, and we can provide electricity. And you have two nanogrid. One is and the battery can store it. One is at the time that we have access, and we use IIT. You have and if you can nanogrid, one do is the historical buildings. The other one is put solar panel and use renewable. IIT. And if you can also do the historical buildings, a lot of places put solar panel and use renewable electricity. We are having the lighting. Also, you will see, which is a lot of places may not have a cable for electricity. Solar, we are and also the lighting in here, which is works with the. So we have a lot of IIT wind turbine, solar, one of the leading and also campuses in here in energy management. So we have a lot of conservation is, or on the other one of the leading campuses in energy management, conservation center, which is or on the other word macro grid. Also, we look at future. We think future is not center, which is a part of every community. Some of them also we look at future electricity. We think some of them may produce electricity. Every community. Some of them may produce. Some of them they may use electricity. Some of them may produce electricity. Some of them may produce sometimes and consume. Some of them may produce. Some of them may and we need produce center. DC, under some of them may produce AC. We have the whole group. We need synchronizing the whole center and seeing that that's what Professor Zhang's leadership means. Some of the energy in each community will be synchronized by that community and seeing that that's able to communicate with each other. Means some of the energy in each community will be produced by that community. Future energy should transfer means that each community that is part of the energy they produce. Part of the energy transfer means that each community should be part of the energy synchronized. Otherwise, everybody produces energy during the sunshine, and all these things should be during the night synchronized. Needs otherwise, so everybody produces energy during the sunshine and energy storage. And during the night, everybody needs that. So we need our synchronization, area transition of fuel in natural gas and biofuel, as I talked to you, and. Do you know that area transition of this piece of rock is burning is not magic, as I talked to you. It's called Hydrate. And do you know that 1% of this piece of rock is burning is not magic? It's called Hydrate as a hydrate. Do you know that 1% of the 100 years of today's U.S. natural gas demand entrapped as a hydrate? We have more is sufficient hydrate for the 100 years of today's U.S. natural underneath gas the ocean in the thermophrost area than entire fossil fuel. underneath the ocean.
The good thing is that it's natural gas.
Permafrost area
means that
then
for hydrogen, one
fossil
carbon,
fuel, much better than oil, much better than
and good thing is that it's natural gas. Means that
what
for
do we
hydrogen,
do?
one carbon,
Much better than oil,
use it.
much
Well,
better than
difficult.
It takes a lot of time and effort to
So
do
what do we do?
So
another thing is that
use it.
you
Well,
it's very difficult.
Takes a lot of time.
It's very
and
difficult to do that, and there's a lot of effort has been done.
Another
to
thing is that
this is
you
one of
have
the
seen,
examples
in the thermofrost area.
It's very difficult to do that, and there's a lot of effort has been done
try
to do.
to
This is one of the examples in the thermofrost
reducing
area
the pressure
that we
at
go
the-
to different
at
zones
the
and
wellbore
try to extract more natural gas.
by reducing
Another
the
thing that you
pressure
hear
at
probably a lot
at
is
the
fracturing
wellbore
to
there
extract
is a
more natural
tremendous
gas.
amount of natural gas resources.
Another thing that
However,
you hear
they
probably
are
a
very
lot
shallow.
is fracturing. And the shallow
There is a
resources, if you want to
tremendous amount
produce
of
from the
natural
well
gas
itself,
resources.
it's very
However,
low.
they are
Therefore,
very shallow.
you have to drill
And
horizontally.
the shallow
Means
resources,
go
if
down
you want to produce
and
from the
drill
well
horizontally
itself,
and
it's very
fracture
low.
Therefore, you have to drill
Therefore,
horizontally.
the
Means
surface
go down
area that
and
gas
drill
will come
horizontally and
will
fracture
increase significantly.
100,000
Therefore,
times.
the surface
And
area
makes the production
that gas will
economical.
come will increase significantly.
There is
the
100,000
advantage, disadvantage,
and
when
makes
you
the
fracture
production
here.
economical. The fracture
But,
could come,
there is
and the
everything
methane
has
can,
advantage, disadvantage
to the
when you
surface, and methane
fracture
can
here.
come to the surface,
and methane comes to
fracture
the
could
surface to
come,
the air is
and the methane can
5 to 10
to the
times worse
surface,
than
and methane
CO2.
can come to the surface,
So we have to
and
be very
methane
careful.
come to the surface to the air is
Then
when you
5
use
to 10
water
times
and
worse
other
than
chemicals for
CO2.
fracturing, we
So we have to
bring
be very
something from underground to the surface.
Then
And we when you use
surface,
water and
there's a
other
lot of
chemicals for
environmental
fracturing,
impact that
we
have to
bring something from
take care of.
underground to the surface, and we contaminate surface.
So
there's a lot
that
of
is the
possibility. That's the best way to
take care
move
of.
to the future renewable energy, because
So
it takes about
that is the possibility.
That's the best way to move to the future renewable
But
energy.
on the pathway
Because
there,
it takes
it's
about
better
to
to
use
30
natural
to 50
gas
years to
with more
completely have
hydrogen than
renewable
anything
energy.
else.
But
And natural
on the
gas
pathway there,
could be
it's
used
better to
and
use natural
remove the
gas
carbon from
with
natural
more
gas
hydrogen
and
than
use the
anything
hydrogen.
else.
And
there
natural
are
gas
processes
could
developed
be
in the
used
US and
and
Europe,
remove the carbon
in
from
Europe
natural
to
gas
do that.
and use the hydrogen.
And there
Another
are
thing
processes
is that
developed in the US
use
and
the
Europe,
in Europe to do that. Plant or energy. Another thing is that they use the biofuel. Plant or energy means
if
that
you use the biofuel,
means that we put the crops there and take it out
biofuel.
and process it and get the
water.
oil.
Wait a minute.
If you use
The
the
crops
biofuel,
needs
means
the-
that we put
the
the crops
water,
there and take
and
it
water
out
could
and
be much more
process
critical.
it and
Water
get the oil.
is more
Wait a minute.
critical.
The crops need
things
in the world
the
than energy.
water.
And water could be much
In
more
the,
critical.
Middle
Water
East,
is more critical.
It's very expensive.
Things
In all over the world,
than
it's
energy.
become very expensive with population.
In the Middle East. Therefore,
it's very expensive.
In all over the world,
and also
it's become very
competing the
expensive with
land for
population
energy
growth. Is the land for the therefore it's compete and also competing the land for
production of the
energy
food.
is the land for the food for the animals feed. Therefore, we will have a
Production of the
severe
food.
impact on the
and the food for the animal,
and should be a balance.
Therefore,
on production for energy,
we will have a
production
severe
for food.
impact.
So we don't want
on
to increase
the price of the food
and should
when
be a
people
balance
needed
on
more than
production for energy or production for food.
And water.
So we don't want to
because
increase in order to
the
grow
price of the
something,
food
you
when
need
people
fresh water.
needed more than
Therefore,
energy.
we are focusing at
IIT
water on
because
algae. In order to
This
grow
is the
something,
reactor
you need
which
fresh
takes the
water.
kinetic data.
Therefore,
and
we are
really
focusing at some of the
IIT
algae
on
fuel. Algae, the good
This
thing
is
is
the
the
reactor
reactor
which
which
takes
takes the
the
kinetic
water. It is
data and
salty
really
water we
the
can use
actually
from ocean.
some of the algae
Great.
fuel.
We can use that one
the good
from
thing
the
is
ocean.
it doesn't need
and
sweet
then
water. It
grow
is
algae
salty water we
and
can
use
from
algae
ocean.
as a fuel.
Great.
Wow.
We can use that
This
one
is
from the ocean
part
and
of a
then
small solution.
grow
It's not
algae
solution to everything.
and use
but
algae as
we
a
have to
fuel.
do all these things
Wow.
together.
This is another thing is
Part of
water.
a small
I talk a
solution
lot
is
about
not
water.
solution to everything,
What are the
but
ways
we have to do all
use
these
water
things together.
is desalination.
Another
Means
thing is water. I
take
talk
the
a lot
salt
about
out of
water.
What are the
water in
ways
the ocean.
to use water?
And that one
is desalination.
basically,
Means
will be done by the water in the ocean. This process expensive, need a lot of energy. Basically, if you combine solar energy, will be done by the it will be great. By the way, this process expensive, need a lot of energy. If you combine solar energy, we have more solar energy coming to the earth. By the way, then there are a lot of processes is trying to use solar energy several times. We have more solar energy coming to the earth. The concentration of energy we need from the sun is very low times. But because otherwise we would have been burned and melted in this planet. But it's very low, and we have to concentrate very low. Because otherwise we would have been burned and melted in this planet. But it's very low, produce a lot of waste. We have to concentrate. We have to use another thing is that and gasify. We produce a lot of waste. We CO and hydrogen, and basically our waste and produce hydrogen, and gasify and gas produced at high temperature CO and hydrogen turbine, and basically produce hydrogen. Do the recovery of the gas produced at high temperature to run a turbine, basically, and if it goes to the water, the recovery of reaction, we have to get the recovery. Basically, CO2, if it is goes to the water that I talked before and reaction, the hydrogen, we have to get the recovery. We have absorb CO2. Really, the process of burying all the release the hydrogen waste. So underground, we have eventually the methane can comes out, and instead of burying all the negative impact, we have to look at underground, which eventually the methane can come out. Also, waste gasification, we have a lot of we have to look at the biomass gasification and also waste gasification. We have a lot of projects. Renewable energy, looking at modeling. This cartoon will show. Okay, we can get from sun. Renewable electricity, electrolyze this cartoon with hydrogen. Okay, the hydrogen we can get from sun, get the electricity, the consumption, electrolyze it, and produce hydrogen. Give the hydrogen use to produce the consumption, the energy of the fuel, and the electricity, and give it back. Use the so directly can go produce the energy, or can use hydrogen and the electricity hydrogen and give it back. Can be used in fuel cell generated electricity, or directly can be used as, or can use hydrogen and then hydrogen can be used in fuel cell generated electricity, or directly can be used as electrolyzer is one of the areas that we produce hydrogen. We can use the different kind of processes, but electrolyzer is one of the areas that we produce in the hydrogen economy. We can use different kind of exhaust of this bus, explaining what will be hydrogen plus oxygen will give the hydrogen economy, and only water comes out. Exhaust of this bus that's will great. Be hydrogen plus oxygen will give water, and solar energy. Solar energy, key energy of the future. That's great, but it's not. Intensity is not solar energy. Solar energy. This red one shows high intensity of the future, but in different parts of the world. Intensity is not good everywhere. We have this red one shows high intensity, and in different parts of the world, in the places like Chicago, which have a lot medium small amount here, intensity here, and again we are using in the places like Chicago, and it is reasonably which is efficient, medium, but all the here, islands in the world, using Australia, solar Africa, energy, South America, all these places in the Middle East, all they don't have to islands in the world, the energy, Australia, Africa, find South America, energy storage, all these places in the Middle East, the solution. They don't have to use solar energy. We can use a lot of things. One of the things is energy storage. Solar concentrated power means we put a lot. We can use a lot of things. One of the things mirror on the top. Solar concentrated power. Means we put a lot, like all these solids or something. Focus this mirror on very high temperature, and use this high temperature to generate steam, like the solids or something. And this steam, very high temperature, and use this high temperature to generate steam, or directly use for any process. And this steam can come instead of run a turbine heating fossil fuel, use concentrated solar, or directly use for any processes. That slides from one of my PhD students. Instead of using the concentrated solar coming here, this is the kind of cartoon of experiment. Slides from one of my PhD students here, using the concentrated solar coming here. This is the kind of solid which absorb a lot. Concentrated solar here, and then heating up temperature. As a function of time, you can increase that absorb and store energy at high temperature in a packed bed of solid. And blue is lower temperature. As a function of time, you can increase that and store energy in a packed bed of solid. Wind speed. This is the different places, and the wind speed of 20 miles per the wind, 9 meters per second. Wind speed. This is the different places, and you will see that
of the red places, 9 meters per second, they have a significant amount of wind. And you will see that
for the wind energy.
The red places,
lower wind is not good, but
they
also
have a
we need
significant amount
continuous
of wind.
And good for the wind
at a
energy.
certain range,
Lower wind
because
is
we
not
design
good,
wind
but also
turbine
we need
over the range of
continuous
RPM.
wind.
Again,
And the wind
at a certain
is
range,
a solution to a
because
lot
we
of
design
places.
wind
And
turbine
if you look
over
at
the
United
range of
States,
RPM.
northern
Again,
Texas, the wind
places
is a
the
solution
middle
to a
part
lot
of
of places.
the United
And if you
States,
look
we
at
can
United
produce
States,
significant
northern
amount of wind
Texas,
energy.
these places,
The middle part
we have a lot of
the
research
United States. We can
at
produce
IIT. We have
significant
one
amount of
wind turbine
energy.
at the campus of IIT, another one in
We have a lot of
Greenwich,
research
Illinois.
and
At
we
IIT,
have a lot of
we
research
have
going
one
on
wind turbine at the campus of IIT, another one
in the
in
School of
Greenwich,
Architecture,
Illinois.
effect of
And
putting
we
the
have a
wind
lot of
on the
research
tall
going
buildings
on.
to
Also,
see
in the
in the School of
computational, we look
Architecture,
at the effect of rain,
putting the wind on the tall
and the effect
buildings.
of snow.
Also,
because Chicago
in the
has
computational, we look at the effect of rain.
We are doing a lot of
study
the
in
effect
this
of
area,
snow
right?
on that, because Chicago has
give you an example.
This is the computational.
We are doing a lot of study in this area,
calculation. And you will
give
see
you an
this
example.
is when there is no rain.
This is the computational fluid dynamics.
When there is a rain
calculation,
and you will see
energy output
fluctuates.
And we have
when
to design the
system in order to take care of this fluctuation.
Energy output fluctuates.
And simply, when it is,
and we have to design the system in order to take care of
there is no rain on it. But when it is flat,
going up and down,
it is
there
peak
a lot
when
of
it is
rain.
straight.
See,
because
there's
there is
a lot
no
of
rain
on the
but
top
when
of
it
the
is
system,
flat,
going
and
up and down,
carry
there
all
are a lot of rain.
See,
so there's a lot of rain on the top
because of rain or snow,
and it has to carry all this rain.
And this is a very interesting.
So the fluctuation of
calculation
because of
that
rain
we
or
had,
snow,
which help to design
is significant.
And this is a very
associated with wind turbine
calculation that we had, which helped to design of the system associated with wind turbine. We have two kind of research are being done at IIT. One is looking at the
energy
storage
and sodium.
We have two kind of research are being done at IIT.
These are the
lithium and sodium batteries.
Looking at the lithium and sodium
batteries.
Work with
these are the lithium and sodium batteries.
Look at the sodium
plus lithium is that there's a limited amount of lithium in the world.
The reason
if you find
sodium
batteries as efficient
is
as
that
the lithium batteries,
there's a limited amount of
which
lithium
work for sodium
in the world.
But if you find
another one
batteries
is
as efficient as the lithium battery,
airflow batteries,
which work for sodium, that's a breakthrough.
You work with the
another
with
one
the stream
going
through
the
anode
and cathode.
Airflow batteries,
two separate project that
you work with the stream
again,
going through the
I told you another
cathode.
project that
and
we have at IIT is urban agriculture.
That
urban agriculture is very interesting. I told you another project that we have at IIT is urban agriculture.
What is the good
urban
things?
agriculture is very interesting because
consume a lot of energy
you create your own
CO2
food by transporting.
What is the good things? First of all, you don't have to consume a lot of energy
create the green area in the
by transporting it to the city.
Thirdly, if the people of the community
that
working together
the green area in the
and
city.
creating food for themselves,
Thirdly,
that would enhance the sense of the community working together
and sense safety
and creating food for themselves. That would enhance the sense of the community.
First, we look at to see
and sense
safety
that we
bring
grow
the safety
in the
community.
city of Chicago. Is it as good as the thing that we grow
First, we
somewhere
look at
else?
to see
way away from
that
the
we
city.
grow
in the city of Chicago.
food safety is
as
one of
good
the
as the
issues
thing
that
that
we're
we grow
studying
somewhere
on that.
else. And
Way away
initial
from the
results shows very interesting.
So
that
food
there is
safety
not
is one of the
significant
issues
difference
that we are studying
as
on
far as
that.
food safety.
And initial results
again, second
shows
thing is
very
that
interesting
we don't want to put the pressure
there is
on
not
the
energy
significant
of,
difference
consumption
as far
of
as
the
food
city.
safety. That's the reason everything.
Again,
use
second thing is
solar
that
energy
we don't want to put the
or
pressure
energy
on the
farm
energy
that we
of
have at IIT,
consumption
which is
of
an
the
example.
city.
That's the reason
farm.
everything used.
Therefore, the
solar
water.
energy or
We don't want to
energy
put
of the
pressure
farm
on the water.
that we have
And
at IIT,
we use the
which
water
is an
consumption
example
or
of
something.
farm.
Therefore, the water. We don't want to put pressure on the water and
keep the
we
water
use the
and
water
reuse
consumption or something. The other thing is that
water
we don't want
collection,
everybody
the rain
travel
collection
and
or
water
something,
the
keep
the
the water
farms.
and reuse.
And traffic will be
The
unbelievable.
other thing is
now
that
is
we
bad
don't
as
want
it
everybody
is.
travel and
So what we
water
do, we put the sensor
farms,
and with
and
your cell phone in your hand, you can
unbelievable.
control,
Now is
irrigate
bad
it at the
as it
time you
is.
want. Or
So what
if
we
you
do,
don't want
we
to
put
do
the
that,
sensor
and with your cell phone in your hand, you can control. Put the level of moisture. At the time if the level drop, or you can even don't want to do that. Good things about this is we found out that different crops put the level of moisture. If the level dropped, therefore you don't overwater. Good things about this is we found out that different crops need the different moisture. Therefore, you don't overwater. And some will be no traffic because optimize if you want the consumption and just look at it, but these are the issues. Will be no traffic because I think the urban agriculture, the camera and just look at it, but will be these are the issues and boundary conditions. Will grow for the future. I think the urban agriculture is something will be. I will grow. I think I had 45 minutes and I'm right on time. Okay. What did I say? I did not give you any thing. I had 45 minutes and I'm right on time. Silver bullet to solve energy and sustainability. What did I say? I did not give you any because our pathway to net zero society and sustainability is different at different locations. Because our pathway to net zero society is different at different available resources. For example, different regulations. If you are looking at the places with a significant amount of wind energy available resources, is a good solution. For example, if you are looking at the places with a significant amount of wind energy is a good solution. If you are looking, you don't have either of them. At the places with the high density of solar conversion of the waste. Maybe if you are looking at other, you don't have either of them. Maybe biomass. You have to use some hydrogen of the waste as an energy. Maybe transported from different other places. Things will be the solution. So it's not a single solution. Some hydrogen. The whole idea is based on least cost strategy. So it's not about single solution, but the whole idea is based on least cost, which costs a lot of money. People are not going to do that. So if you go to the gas station and said this costs a lot of money, people are not $10 per gallon, and which is very good. So if you go to the gas station and said this pump will give you fuel, and the other one per gallon is $2.50, but it is from oil, petroleum, no carbon, good fuel, and the other one is $2.50, but it is from oil, petroleum, the least cost and strategy in decarbonization pathway is the money to do that. Therefore, the least cost and also we cannot do it in decarbonization on the price of other things is the must. It should be look at but also we cannot do it on the price of other food things. Availability. It should be human well-being. We cannot. We look at the generator energy and food availability from the land, human well-being. That much we cannot hurting the food, generator energy. So this it should be in the overall context that much of which the well-being hurting the food and other things. So these, although it should be in the overall context of the well-being of the human beings, but it's the solution. The problem is global. Everywhere because it's a function of location, time, technology. It's and the solution lifestyle people is local. Trying to use because it's we have to really location, look at the time, technology, and the lifestyle people are different solution at different location. We have to really this global, look at the way global problem and the function different of time solution and at different location to this and also global problem between the technical, and the function of time and technology, which is sustainability, and also interlink between the sustainability, economical, and environmental. On three legs, they said social, is environmental, and technical, and sustainability said that. So on three legs, they saying that social, interlink, environmental, all these things, and technical, and also economics, because it should be acceptable. What we're saying that interlinkage between all these things are very critical. I think at this stage, because it should be acceptable. My lecture is by the society. Finished. You can always look at my first slide. I think at this stage and send me email. My lecture is if you have any questions. You can always. Again, it is Arastoopour and send me email at if you have any questions. Again, it is Arastoopour at iit.edu. Thank you.